Hello everyone, welcome to the How series. We are beginning this hands-on workshop, Programming and Optimization for Intel Architecture. Today, session 1. This course comprises 3 modules. Module 1, Programming Models, I like to call how to execute something, and we will focus on the general properties of Intel architecture and also on specific features of certain models of Intel processors, such as Xeon Phi, and how to express programmatically the programming of coprocessors, bootable processors with high bandwidth memory, and OmniPath fabric interconnects. Module 2 is called Expressing Parallelism, and I like to call it How to Run Something in Parallel. We will talk about programming frameworks for expressing data parallelism and vectorization, for expressing task parallelism in shared memory and multi-threading, and for distributed memory computing with MPI. We will not focus on performance optimization that much in Module 2 because we have Module 3, where we will revisit scalar tuning, vectorization, multi-threading, memory access, and discuss them again from the point of view of performance optimization. This course has a web page, and you can click this link to go to the latest How series page, and there, with your free Colfax Research account, you can download the slides, the PDF documents that I'm using, also code of all exercises. You can watch recorded video of presentations, and you can ask questions during live presentations in a chat. For more workshops, check out this page, but the chat, let me focus on that. The chat is at the very bottom of the page, and you need to be logged in. And once you're logged in, you can post questions, say hello, or ask technical questions during the presentation, and we will address them live during the presentation. For more extended questions, we have forums, and you can navigate to forums from the main menu or by clicking this link. By the way, when you download the slides of the presentations, all the links here are clickable, so click to open that page in a web browser. This is a hands-on workshop because we offer all attendees free access to the Colfax cluster. This cluster invitation comes from this email address, cluster@colfaxresearch.com, within an hour from registration usually. And in the cluster, you have access to general purpose Intel Xeon processors and to 2 varieties of Intel Xeon Phi coprocessors and processors. You can use the cluster during the presentation to try and follow along with my demonstrations. You can also access the cluster at any other time to run exercises, to experiment with your own code, and learn in this way. And before we begin the technical part of the presentation, I'd like to point you to Colfax Research. You no doubt have visited Colfax Research to register for the workshop, and there you can find a wealth of information about parallel programming with a focus on Intel architecture. There's publications, including white papers and research publications, demonstrations, video recordings, interviews, and so on. It is all free with a free Colfax Research account. Well, that said, we will begin the presentation, and if you have just joined us, for questions, please go to the chat box on the course web page. I'm going to talk about programming practices called modern code, and to justify them, I'd like to outline modern challenges. We are going to talk about high-performance computing, and it is used everywhere. For example, in natural sciences, it is used to predict the properties of new materials. Medicine uses high-performance computing for high-fidelity medical imaging and for cancer treatment planning. The energy sector uses high-performance computing, for example, to optimize the efficiency of wind turbines and to optimize the extraction of oil from oil reservoirs. Environmental studies use HPC to model climate and to predict weather. In manufacturing, computing is used to optimize the fuel efficiency of cars and aircraft. Data analytics makes use of high-performance computing to make marketing smarter and more targeted. This is done through the use of artificial intelligence, and artificial intelligence is really booming with the help of deep neural networks, which of course rely on high-performance computing. Financial applications include, of course, risk analysis, and it also relies on HPC. Whichever field related to computation you come from, you are probably here because you're interested in performance or speed. And in fact, performance means different things to different people. Some people want shorter time to insight, meaning they want to solve their problem faster. For some people, performance optimization means better power efficiency. This is, of course, important for the largest consumers of computing, such as computing clusters, which have tremendous energy bills. It is also important for computing on smaller devices, for example, battery-powered computers and cell phones. Performance optimization may also mean reduced hardware costs. If you need to solve a certain problem, for example, you need to drive a self-driving car, then optimized performance means that you can reduce the cost of the hardware needed for computing that comes with this car. And especially for people in natural sciences, no problem is big enough to be satisfactory. So performance optimization allows you to tackle greater problem sizes. And there seems to be no problem because computers seem to be getting faster with every new generation. But we will see in this course that there is a prerequisite for excellent performance on new computing platforms, and that is optimized software. This is the focus of this course: how to optimize software so that outstanding modern problems port well to novel computer architectures. To understand what you need to do as a programmer, it is useful to understand how computers are getting faster. And fundamentally, they get faster because of a trend known as Moore's law, and that trend is increasing number of transistors with every new generation of processors. Every 2 years, the number of transistors approximately doubles. You can see that this trend is spectacularly exponential over the past 5 decades, and it was predicted in the 1960s. This trend is made possible by the ever-improving transistor technology. Transistors get faster, they use less energy, you can clock them at a higher clock speed, and you can fit more of them in a certain power envelope. However, not everything is so simple. You can see that there's other trends that I will refer to in a second, and they are not exponential. They have a bend or even a plateau, such as with the clock frequency of processors. Why this is happening and what you as the programmer need to do about it is what we will talk about in the next few minutes. Computers are getting faster, but as you probably know, for the past decade, the clock speeds are not increasing very much. Clock speeds were the key driving factor in the increasing performance of computers in the past, but not anymore. Most of all, this is due to the hitting of a power wall. If you have a traditional cooling solution, a processor with a heatsink and a fan blowing air on this heatsink, then there is a limit of how much power you can extract, how much heat you can extract from the processor. For modern processors, the size that they are, this cooling limit is approximately 150 watts per socket, and it is achieved at roughly 3 gigahertz clock speed. If you want to go past that limit, well, you could invent better cooling solutions. For example, liquid cooling is one of the options. And how about liquid nitrogen cooling? Watch this video for this thing in action. Yes, it can allow you to increase the clock speed, but not by orders of magnitude. Certainly not 2x every 2 years. And even if you do that, your cooling solution becomes impractical. Your cooling solution also consumes power. And now you have to worry about extracting not just the power of the processor, but also the power of the cooling system. And sometimes, like in this exotic project Natick, you can solve the cooling problem in a cheap way. For example, enclose the data center into a steel barrel and lower it to the depth of the ocean. That's free cooling, but of course this is not for everyone, certainly not for desktop computing. So something else needs to be done. Moore's law still holds. Every new processor generation gets more and more transistors. And what you do with these transistors, not you, but what processor engineers do with these transistors, is they make processors smarter. And I will talk about several ways in which processors get smarter by using more logic, and one of them is pipelining. Pipelining implements instruction-level parallelism. With pipelining, you can run multiple instructions at once. And this is done because the instructions are broken down into micro-operations, and there is separate logic for each type of micro-operations. If you have multiple instructions running different stages of the pipeline at once, you can run them concurrently and in this way speed up your calculation. What does it mean to you as the programmer? Well, not much, because pipelining is done on the processor level automatically. You don't need to do anything to take advantage of it. At the same time, there's only so many possible pipeline stages, and there are possible conflicts between instructions. Not all instructions can be executed concurrently. So pipelining is largely at its limit with the modern processor technology. Another form of instruction-level parallelism is superscalar execution. This type of parallelism also uses extra transistors to implement extra logic and run multiple micro-operations of the same kind concurrently. The same idea. You as the programmer don't have to do anything. The processor takes care of parallelizing your application automatically. But the more you want to parallelize, the farther up the instruction stream you have to look, and it requires extra resources. So at some point you hit the point of diminishing returns, and it makes no more sense to increase superscalar execution capabilities of processors. At the same time, this technology exists in modern processors, and your program takes advantage of it automatically. There is also a great way to overlap communication with memory access. And it is absolutely necessary, because these days computers are hitting what's known as the memory wall. The memory wall comes about because even though the floating point, the arithmetic capabilities of processors increase exponentially in time, memory bandwidth and memory access latency is not increasing as rapidly. So in the past, it may have been quick to access memory, but it could have taken a long time to run mathematics. Now, in most architectures, memory access is much slower than any arithmetic operation. In part to compensate for it, modern processors support out-of-order execution. Hardware reorders instructions in the instruction stream so that you can minimize memory access latency by allowing other instructions to execute while one of the instructions is waiting for memory access. And this is not just for memory access. You can also do out-of-order execution by masking low latency in-core operations with operations that use other parts of the hardware. Again, to you as the programmer, it means nothing. You just keep running your software and it automatically runs faster. But even if you're not bottlenecked by memory access today, you will be in the future. And out-of-order execution will not be able to fill the gap automatically if your memory access is order of magnitude slower than computation. So how are processors getting faster? These days, the trend is in the parallelism, but the kind of parallelism that requires programmers' action. In Intel architecture, there are two concurrent forms of parallelism: multiple cores and vector instructions. Cores implement multiple instructions on multiple data elements, or MIMD parallelism, and vectors implement single instruction on multiple data elements, or SIMD parallelism. What this means is that when you have a processor, you have multiple processing elements, cores, and each core can run its own program on its own data. This program can be a thread within a process, or this program can be a separate process. It doesn't matter. Cores physically share memory. Within a process, they also share the virtual memory address space, but they can run completely independent programs. Inside of cores, there are vector processing units which can run a single stream of instructions on multiple data elements at once. This type of parallelism has not so far reached its limits, but to you as the programmer, it is very important to realize that the usage of multiple cores and the usage of vectorization is not automatic. In the case of cores, you alone are responsible for teaching your program to use cores, and with vectorization, you share the responsibility with the compiler to make sure that your math is executed using short vectors. Parallelism is the path forward, and parallelism has existed in computers in the past. After clock speed drive has reached its limits, you could still enjoy faster and faster processors without changing the software, because there was automatic parallelism and out-of-order execution, and it kept getting better and better, and it slightly is getting better these days too. But mostly, processors become more parallel through the use of cores and vectors, and you, as the programmer, or your software, must catch up. Otherwise, you will not be able to take advantage of performance offered by modern processors. In this course, we will talk about 3 layers of parallelism. We will talk about, on the lowest level, vectorization. And this is the capability of a single-threaded program to apply a single stream of instructions to multiple data elements at once. We will talk about another layer of parallelism, which is multi-threading. To you, the programmer, you deal with threads, and threads on the hardware level are distributed across multiple cores. And we will talk about cluster computing, where your program already knows how to use multiple cores, and now you teach it to use multiple independent machines connected together into a network. The programming frameworks we will study are automatic vectorization, including guided vectorization, OpenMP for multi-threading, and MPI, message passing interface, for distributed memory computing. All of the demonstrations that I'm going to run apply to Intel architecture, and I will also make the claim that the general principles that we teach apply to non-Intel processors as well, as long as they have similar building blocks: cores implementing MIMD parallelism, vectors implementing short vector support, hierarchical memory, and potentially high-performance interconnects in a cluster. And Intel makes a variety of processors. You probably have an Intel Core or an Intel Atom in the computer that you are watching this presentation on. We are going to focus on enterprise class processors branded Intel Xeon. In addition to these general purpose processors, which are very similar to each other, Intel makes specialized processors branded Xeon Phi. They are balanced for computation, and I will discuss them in a minute. They include bootable and coprocessor versions of CPUs. And for reference, I'm also including network interconnects. We will play a little bit with the Intel OmniPath architecture, which is a high-performance interconnect for clusters built by Intel. And I will mention the Visual Computing Appliance, the upcoming Nirvana platform for deep learning, and the deep learning inference appliance built based on FPGAs. So not everything Intel is x86 architecture. There's also exotic, well, as of today, exotic solutions that are likely to become mainstream in the future. We are not going to talk about these technologies in this course, however. So what are Xeon and Xeon Phi processors? A Xeon is a brand name, and if you take a look at a Xeon processor, it can be one of the many microarchitectures. But the idea is that this is the enterprise class CPU where you find the greatest number of cores, the highest memory bandwidth, and server reliability features. In addition, you can find Xeons in two-way or four-way form factor. This means that instead of one chip, you can install 2 or 4 chips on the same server board. To your program, it will look like doubling or quadrupling the number of cores. However, it makes your system NUMA, non-uniform memory architecture. We will talk about programming implications of that. But the idea is you can use the cores of not 1, but 2 or 4 processors at once. They are general purpose processors. They will handle arithmetically intensive calculations very well. They will also compensate for possible inefficiencies in legacy code, and they will work for running. They will work well for running non-computational applications such as web servers. It is very important to stress that general purpose CPUs are not serial. They are highly parallel. If you take a look at the latest as of mid-2016 Xeon processor, E5-2699V2, it has 44 cores with two-way hyperthreading, so you can efficiently run 88 threads on it. And these cores are resource-rich, which makes them forgiving to suboptimal code. The theoretical peak performance of this top-of-the-line Xeon is 1 teraflop per second in double precision. Teraflop stands for 1 trillion floating point operations per second. And this is in double precision for the fused multiply-add operation. If you do a different kind of math, the theoretical peak is different. The memory bandwidth that you can expect on this two-way processor is up to 154 gigabytes per second, as measured by the Stream benchmark. Let's contrast it to a Xeon Phi processor. Well, first generation Xeon Phi, first released in 2012, was based on the Knights Corner architecture. Excuse me, and it was available only as a PCI Express add-in card. It means that you had to have a host, and you install this card into a host system powered usually by a Xeon. Xeon Phi is specialized for computing. What does it mean? It means that it is highly parallel, well, just like Xeon, but maybe more parallel, and it is balanced to do more floating point operations than the Xeon at the cost of being less forgiving. It means that if you have legacy code, it will not run very well on a Xeon Phi. It is not a solution for everything. It is a solution for modern applications that take advantage of cores, vector instructions, and memory hierarchy. Its theoretical peak performance in double precision is 1.2 teraflops per second. And you may say this is not much greater than the Xeon that we saw on the previous page. But I want to stress that on the previous page, we saw a 2016 technology. And this is a 2012 technology. So 4 years earlier, Xeon Phi had a greater theoretical peak performance than a Xeon that followed. And so the same goes for memory bandwidth. And this is the bandwidth of the CPU on the board accessing the memory modules on the board. They are based on the GDDR5 technology. Since then, Xeon Phi has been upgraded, and in 2016, Intel introduced a bootable version of Intel Xeon Phi processors. And now this is no longer a PCI Express add-in card. It is a processor that controls memory, that controls file I/O, and it controls networking. You use it as a regular CPU, but you get up to 72 cores with 4-way hyperthreading. And it is also balanced for computing. So it is less forgiving than the Xeon, but in a smaller power envelope and for a smaller cost, it can deliver, it has the theoretical peak performance 3 times greater than that Xeon. And the same goes for bandwidth, and this is memory bandwidth of the cores to the on-package memory. And this memory lives on the chip. It is based on the MCDRAM technology. Also coming up is the coprocessor version of Xeon Phi, 2nd generation. It will also be manufactured as a PCI Express add-in card, and this is a great solution. If you do desktop workstation level programming, so you want to have a powerful Xeon to run a computer-assisted design or visualization or legacy applications, and install one or several Xeon Phi coprocessor cards in it. So this is coming up, not available just yet. Or maybe it is available if you're watching this as a recording. I will show you a few diagrams of hardware organization. And I know that most people here are software developers. And I understand this, and I have the same background. So I'm coming from the angle of what's inside the chip that I, as the programmer, have to know. What's going to help me to write better code? And I think one of the most important design factors that you need to be aware of is memory organization. We will look at the memory organization of a Xeon Phi coprocessor, and a Xeon Phi bootable version. First, a two-way Xeon. I say two-way, this is the official term. Sometimes you will also see the term dual socket. Dual socket is just the jargon term for a two-way processor. You see multiple cores, and cores can operate on data that lives in the register file. The register file is very small. It is in kilobytes. And if you want to operate on a data that lives in memory, your core can just request this piece of data from memory. A cache line will be sent to the core, but along the way, it will be cached in the last level cache, in the level 2 cache, and in the level 1 cache. So if you address this memory element again, if you do it soon, then it will be fetched from the level 1 cache, which is small but fast. If you traverse a lot of data and you had to evict this original piece of data from the level 1 cache, then you will go to the level 2 cache. It is larger but slower, and in case you don't find the data there, you can also ask the last level cache, which is even larger but even slower, but still faster than going to the main memory. If you're dealing with a two-way processor, then in addition to this package, you have another package on board, and I only show a part of it. So it will be a CPU controlling its own memory. There's a CPU here, didn't fit on the screen. And there is a quick path interconnect between them. It is transparent to the programmer. Transparent means that if your program runs on this core and it wants a piece of data that lives in remote memory, you can just ask for it by address, and it will be sent back and cached in all of the required caches. If you contrast it to a Xeon Phi coprocessor, you will find actually first a lot of similarity. Cores operate on registers. Behind the registers is the level 1 cache, small but fast. Behind them is the level 2 cache, larger but slower. The first difference is there is no LLC, no last level cache. Behind the level 2 cache is the onboard memory. So this is the memory that lives on the card. It is up to 16 gigabytes in size, access latency of order 100 cycles, high bandwidth. I'm here talking about the Knights Corner architecture, first generation of Xeon Phi coprocessors. And this is the universe of your program if it lives on the Xeon Phi coprocessor. There is also the host processor with a tremendous amount, possibly, of on-platform memory. But between your application and that memory is the PCI Express interconnect. And this one is not transparent. To you as the programmer, it means that you cannot just say from this core, give me this memory address. You cannot just access it by address. You have to initiate memory transfer across the PCI Express bus in one direction or the other, and we will talk about doing it either using offload or MPI. And for your information, you can also talk to the driver called Skiff. So this is the key difference. If you want to access large amounts of data, you have to stage explicitly data transfer between the host and the coprocessor. If you have a Xeon Phi which is second generation and bootable, then the situation is neither of the two above. Well, you do have cores with registers, you have small but fast level 1 cache, you have larger but smaller level 2 cache. Again, no last level cache. But living on the package here is high bandwidth memory. It is based on the MCDRAM technology, multi-channel direct random access memory. And it is also limited in size, up to 16 gigabytes. But the bandwidth that you can achieve from it is 3 times that of the GDDR5. So far, very similar to coprocessors. But the key difference here is that access to the on-platform memory, which can be large, is actually transparent. So you don't have to do anything special to move data from the on-platform memory to the core. Your program can just ask for a certain memory address, and the hardware will deliver it and cache it in the level 1 and the level 2 cache. That leaves the question, what do you do with the high bandwidth memory? And you can do one of the 3 things. You can configure it in the flat mode, meaning that you have a special allocator, and the special allocator allows you to put data in the high bandwidth memory, up to 16 gigabytes of it. The second option is using it as a cache. In this case, the operating system does not see the high bandwidth memory, and instead it sits quietly between the level 2 cache and DDR4 and caches data that passes through it. You can also do hybrid, meaning you split the memory, the high bandwidth memory, into two parts, and one part you configure flat and the other you configure cache. And this is a boot time decision to use the flat, cache, or hybrid memory topology. As you can see, to you as the programmer, there are going to be certain differences with regards to how you are going to use a Xeon Phi coprocessor or processor versus a Xeon or something like an Intel Core processor. But at the same time, a lot of similarity. The fundamental building blocks are the same. A hierarchy of caches, multiple cores, and inside the cores, vector instruction support. That makes it possible to talk about what's called modern code practices. The idea of modern code is to contrast it with legacy code, to produce applications that are highly optimized for modern architectures, but not to the degree where they are tied to an architecture. A modern application will also be portable across today's processors, coprocessors, and future-proof, meaning portable to future architectures of Intel-like CPUs. If you've done any computationally intensive programming, you will know that optimized and portable are often in conflict with each other. So how do you find middle ground? How do you make your application both portable and highly optimized? There's two parts of it. First, you need to make your application cognizant of the architectural building blocks, such as cores, vector instructions, high bandwidth memory, and fabrics, but not in a way that ties your program to a particular processor. And this you can achieve by relying on standards for high-performance computing. There are standards for threading, vectorization, and offload, and we will talk about a framework called OpenMP, Open Multiprocessing, where you actually find language extensions for all three. My hope is to convince you in this course that it is possible to write a single code that will be all three: optimized, portable, and future-proof. When we talk about performance optimization and future-proofing, I want to define the scope that we will discuss. We are going to talk about having a particular numerical algorithm and implementing it as close to the underlying computer architecture as possible. Of course, this is not the only opportunity for optimization when you're solving a real-world problem. First, you have to choose an analytical model, and you may make approximations that make your code run much faster. You also have a choice of how to discretize your analytical model, and there too you can make good improvements. You can choose the numerical algorithm as solver for your equations, and there you can find opportunities for performance optimization. We are going to talk about the last level in this pyramid. Given a numerical algorithm, implement it as a program in C, C++, Fortran, as close as possible to the underlying architecture. If we restrict the discussion to this level, then we can formulate a methodology for performance optimization that will produce modern code. This methodology is based on recognizing the building blocks of processors. Scalar tuning is the optimization for the pipeline. Vectorization tuning is the optimization for vector processing units. Optimization of multithreading recognizes the multiple cores found in modern processors. Memory optimization recognizes caches and going to the high bandwidth memory. And together, these four areas of optimization form node-level optimization methodology, optimizing code on one shared memory processor. If you want to go one step further and do cluster-level optimization, there you talk about the optimization of communication across the network between machines. I want to make a disclaimer that communication is sometimes a word used to talk about memory traffic, but in this course, communication means networking. These 5 areas of optimization are based on the fundamental building blocks, and for each area, we have targeted exercises. These targeted exercises, their idea is to expose an optimization opportunity and allow you to do step 1, 2, 3 to see what you can do to improve this code. And we will have focus sessions on each of these areas in the second week. This week, we are going to lay the groundwork for that by studying how to vectorize the code and how to express multithreading and network traffic. I've talked about performance optimization, and I have a few case studies that you can research, that you can read about on Colfax Research, and hopefully they will convince you once again that it is possible to have a single code base for multiple architectures. This first case study we did with Dr. Troy Porter from Stanford University, who had an astrophysical code. It is a library for computing the transient emissivity of cosmic dust grains called HeatCode, and it is a part of a larger project on modeling radiative transfer in the galaxy. So what you're seeing here is a numerical model of the galaxy that we live in. Our sun is somewhere here. We look at the universe from this location and we have sky surveys. And from these sky surveys in multiple wavelengths, we want to infer what does the three-dimensional structure of this galaxy look like. And there are tools out there to study this problem. And when we worked with Troy Porter, we estimated that the project that we were hoping to run would have taken 6 years on any hardware, because there was a limited, it was a case where we had a good algorithm that limited its scalability. 6 years is not very convenient, and we thought maybe if we use Xeon Phi coprocessors, we will cut it down to 2 years or so, then it will be feasible. This resulted in a story that I think is very, very common with people transitioning to Xeon Phi. You begin at step 0, you take a baseline performance measurement, and then you take your code and run it instead of a regular CPU on a Xeon Phi processor or coprocessor. It is often a question of a few minutes or a few hours to port the code. We will see how tomorrow in session 2. And what we saw is that instead of experiencing a speed up by a factor of 3, our code slowed down by an order of magnitude. So the y-axis is performance relative to baseline, but this is a log plot. So our code is slower on Xeon Phi than it is on a regular CPU. Then we started optimizing, and some optimizations that we made were generic. They had to do with the algorithm and nothing, and they were hardware oblivious. But from that point on, we only made optimizations that made the code closer to hardware. And as we went on, performance on Xeon Phi got better and better. It crossed the line of the baseline performance, and we stopped here when we saw no more easy ways to optimize the code. And if you did this comparison, optimized performance on Xeon Phi versus the baseline, the factor is huge, 200x. Does it mean that the Xeon Phi is 200 times faster than the CPU? That wouldn't make any sense. But thankfully, because we focused on modern code, we could take the same exact code that we optimized for the Xeon Phi and run it again on a standard processor. And what we saw is that performance was increasing on the CPU all along. And on the CPU, we also experienced a performance impact, and it was 100x from performance tuning. Some people look at the model of the processor that we were dealing with, and they say, well, okay, you have 16 cores times maybe vectorization, you get in single precision, you get what, 8x, 16 times 8 is 120, something in line with that. But no, what we started with was a multi-threaded code. So we were already using 16 cores of the CPU at the beginning. And even that parallel code, we were able to optimize by a factor of 100 by making it closer to hardware, but in such a way that you can still use it on a different platform. So this is a story of porting to a Xeon Phi coprocessor. Xeon Phi, in this case, worked as a litmus test of our performance. You can read more about it by following this link. Not all legacy code is slow. Sometimes what you might call a legacy code can actually be highly optimized. We worked with Dr. Clifford Addison of the University of Liverpool and helped him to scale a shallow water equation solver, CFD application, computational fluid dynamics, onto a cluster of Intel Xeon Phi processors. The amazing part of this application is that it was written in 1984 at the National Center for Atmospheric Research in Fortran. Then, in 2008, Professor Addison modernized this code, meaning it taught it OpenMP, MPI, and the code also vectorized. And then in 2014, he found us, and we had a cluster of Xeon Phi processors. So he tried running this application without any modification on a Xeon Phi. Back then it was Knight's Corner. What he saw was speed up. The speed up was significant enough to claim that it was a good code for Xeon Phi without any modification. That's a legacy code written back when Xeon Phi did not exist, working out of box on Xeon Phi. But what didn't work quite well is cluster scalability across a cluster. And we helped to optimize, to tweak slightly the parameters in this code so that it was able to scale across a cluster of Xeon Phi processors. It's also a good example of modern practices, but this time in what you might call a legacy application. Another example of modern code is neo-heterogeneous clustering, where you write an application in such a way that it has no idea what it's running on. It has no idea about Xeon Phi, but you can run it on a cluster of regular processors or on a cluster of coprocessors, Xeon Phi coprocessors. Or the third option is on a cluster that is heterogeneous. It contains both CPUs and coprocessors. We have a paper studying that, and this paper actually became one of the exercises in this course. So if you take a look at Lab 411, it is a slightly cleaner version of the same code. The idea here is that we can write the application in such a way that it just passes messages using MPI, and it doesn't care what it's running on, but it has built-in load balancing, this in our case using the Boss worker model, that allows us to scale across a heterogeneous cluster. And if you configure coprocessors in such a way that they get IP addresses on the network of the cluster, you can just send messages peer-to-peer between coprocessor cards, even if they live on different machines. And one more example of modern code practices is middleware optimization. Not every computational application is written in C or C++ or Fortran. Some applications use higher level languages such as Python or MATLAB or R, or as in this case, the Lua language. We downloaded an open source application written by, I believe, a postdoctoral scholar, Andrei Karpathy at Stanford. It's called Neural Talk, and this is an image tagging application. It's fun. It's trained on, it came with a pre-trained data set that allows you to show it a photograph, and it would describe the photograph with a sentence where it recognizes the relationships between objects. For example, this, according to the application, is a black and white cat sitting on a car. Well, on a car is not quite good, but not bad for a toy application. And you can see the man and the woman are sitting on a train, which is actually accurate. This is not the point. The science of this application is not our domain. Our domain is performance optimization. It was written in Lua and based on the Torch framework. This is a framework for machine learning, commonly used, which is built without much concern for the building blocks of the underlying hardware. What we were able to do is to run this application on a Knights Landing architecture chip, a Xeon Phi, and then optimize just the Torch framework so that we experience a 50x speedup. So the inference in this network became 50 times faster. By the way, Torch is now released. There's an Intel distribution for Torch available, and this is optimized for Intel architecture. The idea here is that if you have an application written in a high-level language, sometimes you don't want to do anything with this application, but only optimizing the middleware, the software that interprets your high-level language and runs it on the processor. Only optimizing this can also yield tremendous performance benefits. So hopefully I've convinced you that modern code is a real a good method for ensuring that your application is optimized, portable, and future-proof. And we are going to move towards learning these practices in the following 9 sessions. In session 2, we will talk about everything Xeon Phi, So we will discuss heterogeneous architectures and also NUMA architectures from the point of view of how to write something, how to program in such a way that your application runs on a coprocessor, on in high bandwidth memory of Xeon Phi, and so on. In session 3, we will talk about expressing opportunities for vectorization to the compiler, automatic vectorization and taking advantage of data parallelism. Then continuing expressing the module expressing parallelism is a session on multi-threading with the help of OpenMP. And in conclusion of the week, expressing parallelism on the level of a cluster, we will talk about MPI in session 5. Starting from session 6, we are going to talk about performance optimization. In session 6, there is going to be an overview example. I will take an n-body application written in a way that's not aware of the underlying architecture, and I'm going to rewrite this application in such a way that it becomes aware of multi-threading, pipeline optimization, vectorization, memory traffic, and we will experience tremendous speedups, and we will also scale this application across a cluster. So you will see all of the modules of performance optimization in action. In session 7, we will focus on precision control and regularizing vectorization patterns. So revisiting vectorization, this time from the point of view of performance tuning. In session 4, we are going to talk about multi-threading from the point of view of common issues, how to minimize synchronization, avoid false sharing, and strip mine for parallelism. In session 9, we will discuss parallelism in memory. And we are going to talk about multi-threading again, this time from the memory aspect. So this is an overlap between threading optimization and memory optimization. And finally, in session 10, we are going to focus on optimizing for caches and high bandwidth memory. The plan for today is to demonstrate the cluster on which you are going to work and show you how to run basic applications, show you how to obtain the code of the exercises, and all of that you can do either along with me or offline. Anyway, before we begin the hands-on demonstration, let's declare a 5-minute break. And after the break, we will resume, and I will perform a hands-on demonstration of using the Colfax cluster, which is necessary to start the material of tomorrow's session. See you in 5 minutes. Stay tuned. Okay, let's resume and move on with the hands-on demonstration. I will talk about the Colfax cluster. This is where you are going to run all of our exercises. The invitation to connect comes to you in an email message from cluster@colfaxresearch.com, and it will give you a link with a special code that gives you access to this page. In this page, information is organized into 5 sections: Learn, Connect, Program, Compute, and Benchmark. In the Learn section, you learn about the How series, and here is the organization diagram of the cluster. The most important aspect you have to recognize is that when you connect using SSH, you find yourself on a login node. This is not a high-performance computing machine. This is just for managing your files and compiling applications. To access the Xeon and Xeon Phi processors, you have to go through a queue. And to submit to a queue, you will use the tool called QSub. I will demonstrate it in a second. And your job will go to one of the compute nodes where it will execute and return the results. For your convenience, we are network sharing the home directory and directory opt with all the tools so that you experience the same file environment on the login node and on compute nodes. Also in the Learn section is a table listing the compute nodes that you have in the cluster. There's currently 12. The first 4 have Xeon processors, Ivy Bridge architecture. These processors are two-way, so they have 2 chips. Each package has 12 cores, so a total of 24 cores in each of these compute nodes. 128 gigabytes of RAM, just a gigabit Ethernet interconnect. But each of these compute nodes has a single coprocessor, and you can use these nodes for offload applications. There's also 4 nodes with Xeon Phi processors, 7210. They are 64-core machines with 96 gigs of DDR4 and flat memory topology. In addition to gigabit Ethernet interconnect, they also have OmniPath interconnects. And there's 4 more nodes that also have Xeon Phi processors, Knights Landing architecture, but they are in the cache mode. You have slightly more than 14 days of access. The access termination date is on the front page of this portal. And this is an educational cluster, not for heavy workloads. So by default, we limit job duration to 1 minute. This is plenty of time to study all of the computational exercises that we have for the How series. If you wish, you can request up to 3-minute job duration, and it will still work, but your job may have to wait longer in the queue. And there's a link to the How series. So this was the Learn section. Now, under Connect section are instructions for connecting from a Linux computer, or from a Mac, or from Windows. They are all self-explanatory, but what I want to say is that when you connect, you will use, for example, PuTTY. Connecting means obtaining a prompt in a text terminal. If you are familiar with programming in Linux or on a Mac, this is all you need. If you are not familiar with Linux programming, you can study one of the tutorials that we have on the course webpage, colfaxresearch.com. How series, see tutorials. If you absolutely need graphical user interface, you can connect with remote desktop. For that, we support X2Go, and this is the only protocol, the only tool that we support, although other protocols, with other protocols, it may be possible to connect. If you have any trouble connecting, feel free to ask on the forum. callfactorsearch.com/forums or forum. All of these links will work. The next section is programming, and here is something I will demonstrate. We have programming tutorials, and there's a list of installed compilers and how to compile and run something. Not very hard. Oh. Use your favorite editor, Vim, Emacs, Nano, to create a program. So this is my Hello World application. Well, I find it in the home directory. We have Intel compilers. There's the Intel C compiler. There's the Intel C++ compiler. And there's the Intel Fortran compiler. All of these compilers will work. You can also use GCC, but if you're compiling for Xeon Phi, then use the GCC from opt. I'm sorry, what is happening here? That's not good. I think one of the keys got stuck. Let me try again. Here's GCC. Okay, well, anyway, I have my code Hello World. It is in C++, so I'm going to compile it with the Intel C++ compiler. And if I run it here, it prints what I expect, but this is running on the login node. Don't run computational exercises, computational workloads here. Instead, go to the queue. Well, why is that? Because the processor that we have here is not a high-performance processor. It is actually a virtual CPU with 8 cores, and this virtual CPU is not capable of giving you enough performance to experience parallel programming. And also we have strict limits on how much you can run. For example, we limit you to 120 CPU seconds. So this is so that people don't slow each other down when they run applications. So instead, you should go to the queue. Well, okay, how do we go to the queue? This is actually explained on the Access portal here under Compute. Under Compute, you can find basic job submission, command file submission, and also job manipulation, job parameters, and distributed memory jobs. This is the most involved and maybe the most time-consuming section of the instructions, but it gives you access to a standard tool chain that you find in industry in standard clusters. So this is option 1 of getting to the queue. Pipe syntax. You do it like this, echo. So normally I would run hello, right? So now I will do echo, hello, type qsub. So the command that I had to run, I have to echo this command into the input of a tool called qsub. When qsub launches, it gives me a receipt. This receipt has the job ID, and if I run qstat, all of my pending and running jobs will be shown here. This column is status. Q means queued, waiting for its turn. R means running. In a few seconds, the job will disappear. It actually disappeared quite a while ago, so I run qstat. I don't find anything. So where's my output? The output goes into special files. If I do pipe syntax, the files are called stdin, stdin.e, stdin.o, and these are the error stream and the output stream. The error stream in this case contains nothing. The output stream contains a standard header, the output of my application, and a standard footer. By the way, you can use the timestamps in the header and in the footer to estimate how long the job took. There's some overhead, though, included in this timing. Okay, so this is option 1, pipe syntax. Option 2 is command file. It is more flexible. It allows you to specify multiple commands, job parameters, rename the job, redirect output logs, and so on. You can do all of that in the pipe syntax, but it is cumbersome, so command file is better. So let me illustrate why. Suppose I created a project for my application, and I moved all of my hello applications into my project. So I go to my project. This is where I am. This is what I have. And I try to do the trick with pipe syntax like this. My job gets submitted. But this time, when the job finishes, I will get a receipt that has nothing. And that is because there was an error. No such file or directory. This happened. We ran from a subdirectory. By default, jobs start in the home directory. Okay, so what do we do about that? Instead of the pipe syntax, I will use a command file. I will call it my job. And in the command file, I can specify multiple commands. For example, I can change directory somewhere. I can run hello world. I can also do some diagnostics, for example. This job is running on compute node such and such. So when I change directory, my options are I can go to my project. Well, actually, let's leave it at that. Remember to have some empty lines at the end. Okay, so now instead of submitting a single command, I will submit a script. This is basically the command file syntax. So the command file syntax is like this: qsub my job. Now, in the queue, jobs will be reflected with the same name as my command file. And when I get output, it will not go into stdin. It will go to my job.error, my job.output. You can see that this works. And this particular job is running on this compute node. And it says hello world. If I want to find out what this compute node was, I can type pbs nodes. And in that list, I can find that this was a Xeon Ivy Bridge architecture, this processor, so much memory, gigabit interconnect key, and so on. So all of these properties I can request. I can request nodes with certain properties. For example, if instead of a Xeon I wanted to run on a Xeon Phi processor, I could request one of these properties, well, maybe KNL. Let's see how that works. With command files, I can insert PBS directives. The syntax is like this. At the beginning of the file, you will have hash PBS, and then arguments that are discussed here under job parameters. For example, you can request output redirection, you can change the job name, you can set the path to working directory, you can request wall clock time, or you can request node features. The syntax will be like this. -L requests our resources, nodes, I want one compute node with a Knights Landing architecture. As a proof of what we saw, I will do LSCPU on that processor. There may be multiple parameters. For example, pbs-l n will rename the job. My other job as you can see in the list of jobs, this is my other job. It will still take a second. It's done. Finalizing. And now it went to compute node C5 and 11. The processor is an Intel Xeon Phi CPU 7210 with 64 cores and a total of 256 logical CPUs. That is because it has 4 hyperthreads per core. And if my application knew how to take advantage of these cores, it would have run there. If I wanted to request more than one compute node, I could do that. For example, I could request 4. And let me change what I'm going to run. I will print the following. I will call it my cluster, and I will print this. I am running on such and such host. This job has the following nodes. Nodes reserved. And I will print out the contents of a file called PBS nodes. For my information, I will print this list came from the file PBS Oh, is it PBS node? I'm sorry, I sometimes forget. PBS node file is the correct variable name. Node file. Okay, so I will print I'm running on such and such host, and this job has the following nodes reserved for it. I will type the contents of a file referred to by the environment variable PBS node file, and I will also print the path to this file. It is now running. And here's the output. As you can see, the script was executed only once on one compute node, C5 and 11. But the job reserved 4 nodes for itself, C11, 12, 13, 14. So these 4 nodes didn't do anything. We didn't teach our application to take advantage of them, but it was very convenient to have them reserved because we could use MPI to scale the application across these 4 nodes. And we will learn how to do that in session 5. And the last demonstration that I wanted to make is this. We log in to a login node. There is no SSH access to compute nodes. We can only use the queue to access them. But when a job is running on a compute node, SSH access opens. This is what it looks like. If I wanted to see my job in action, or if I wanted to explore the environment of one of the compute nodes, I could do this. Echo, sleep, for example, sleep up to 60 seconds, qsub, and request one node with Knights Landing architecture in the flat memory topology. While the job is running, I can query which node did it go to. And I can do qstat-f 9715 grep exec host. And this is the host name on which it is running. I can log in while the job is in progress. You can see that the prompt has changed, meaning that I'm on a different login node. And now I'm dealing with an Intel Xeon 5 processor. I have a total of 256 logical processors, 115 gigabytes of memory. That is because, and we will talk about it later, I have access to 2 NUMA nodes, one DDR4 and one high bandwidth memory based on MCDRAM. We will talk more about this in the next session tomorrow. This is useful, for example, if you want to do some sort of a quick debugging or see how much CPU time your program is using. But this access will be terminated when your job runs out of the allotted time. These are the procedures for using the Colfax cluster. If you have further questions, feel free to ask them in the chat or on the forum. Hopefully you will have enough time to experiment. For your experiments, you can use your own exercises, or you can, as I will do now, check out the repository of How Series Labs from GitHub. I think this is the URL. it's not. So let me look it up. Hold on a second. How Serious Labs? I just forgot that Git. No? Oh. And this is git.svn. Okay. Now we are set. After this command, this is the right command, sorry for failed attempts. After this command, you will get a new directory called How Serious Labs, and you can peek inside. We will study the labs in the next few sessions, but you can see that we have targeted exercises for Module 2, which is how to program, Module 3, how to express parallelism, Module 4, how to optimize, and there's Module 5 related to tools, which we do not cover in this particular training. Well, that's that. Experiment with the cluster. Thanks for joining us today. I hope to see everyone again tomorrow for the discussion of everything Xeon Phi. How to offload, how to program coprocessors with native or offload programming, how to take advantage of high bandwidth memory in bootable Xeon Phi, and have a good rest of the day, everyone. Goodbye.